Our key observation is that harmonic isolines play an important role in shape analysis, acting as a high-level descriptor. In this work, we are interested in investigating the boundary value problem for Poisson equation. Then we focus on Dirichlet boundary condition in conjunction with a Laplacian-type system. Our main motivation is to provide a clear understanding of the well-known expression subject to boundary condition. Our work falls into the general problem domain of expressing boundary condition in a variational fashion. Our insight is to exploit the linear algebra mechanism to inject the boundary condition by wrapping the Laplacian matrix. Our main contribution is to rethink the boundary condition treatment by avoiding the traditional weak formulation. A large number of prior work has investigated the problem of defining harmonic fields with boundary conditions. Even if our work builds upon handle-aware isolines, our method differs substantially from prior work in the enforcement of Dirichlet boundary conditions. Mesh segmentation methods also benefit from harmonic isolines. For example, Zhang and coworkers preferred to decomposition the surface with cross-boundary strokes and then to use the simple harmonic field as decomposition support. Majority of previous techniques are based on a weak formulation that introduces penalty terms as boundary integrals. Our work is also relevant to recent efforts in pairwise harmonics. In more details, Zhang and coworkers introduced new shape descriptors based on the isocurves of harmonic functions. In contrast, our contribution is based on a strong formulation by overriding degrees of freedom instead of introducing penalty terms. In this work, we explore the use of an injective scheme as an alternative technique to strongly enforce the boundary condition. We believe our most important contribution is the injection of the boundary constraints into the Laplacian matrix. To this end, we develop a novel mathematical formulation called injective Dirichlet boundary condition. The novelty of our work is an injective scheme tailored for the strong formulation of the Dirichlet boundary condition. We introduced the concept of competitive boundaries for surface isolines as a collection of boundaries brushed over the surface. At the core of our system lies a linear numerical solver that estimates a harmonic field constrained by imposed boundaries. Our technique provides a squared matrix form treatment. Then we obtain a rich set of surface isolines by sampling the estimated harmonic field. First, competitive boundaries are specified. Then, a harmonic field is computed. Finally, isolines are sampled. First, we brush sparse boundaries. Then we solve the wrapped Laplacian system. Finally, we sample the harmonic field. Poisson-based isolines are of great interest for shape analysis. Key to our approach is the ability to inject boundary conditions into the Laplacian matrix while keeping the final system in purely squared form. Defining suitable numerical boundaries with a strong formulation is a hard problem when dealing with partial differential equations. To the best of our knowledge, our method is the first to provide a strong formulation to the problem of Dirichlet boundary condition for Poisson equation. Finally, a promising future work is to explore isoline-oriented applications, like surface skeletization, incorporating our new numerical framework. We would like to exhibit a generalization of our approach whatever the boundary type, for instance, Cauchy or Robin. Thank you for your attention.